Good afternoon, everyone. I hope you're really excited to be programming against Windows Azure. Many of you have already attended the overview talks, which describes all of Windows Azure, another talk, which is the overview of Windows Azure storage. Pablo and I will now do a deep dive into programming Windows Azure tables. So I am a development lead working on Windows Azure tables, and Pablo is a software architect working on ADO.NET Data Services, which is the API we use to access Windows Azure tables. So let's do a quick overview of Windows Azure. Windows Azure is an operating system in the cloud. It provides many essential functionalities that you would want in a cloud application. So one of them is virtualized computation, so you can run your own code on the cloud. You can have scalable storage, so you can access vast amounts of files and structured storage. You have automatic management of your storage nodes, so you don't have to worry about how to distribute your computation or your data if any nodes fail. And you have a rich developer SDK to make accessing all your data very easy. Windows Azure Storage builds upon three fundamental abstractions. It has blobs, which you commonly associate with unstructured storage. It has tables, which you commonly associate with structured storage. And it has queues, which allow you to which provide reliable delivery of messages, which enable rich applications. Finally, Windows Azure tables provide the massively scalable tables. Now, one of the main problems you have when you have a very successful website is that you get lots of data very quickly. And then you end up with the same problems that you have to solve over and over again. How do I spread my data across multiple servers? How do I make sure that if any server goes down, my service is still available? How do I make sure that if a single disk crashes, I haven't lost the only copy of that data? Windows Azure Tables solves all of these problems. The massively scalable tables can grow seamlessly to billions of entities and terabytes of data. They can use thousands of servers as the traffic grows. So if you have any hot structured entity, you can be guaranteed that it will go to a server where it is highly available. It is also durable, so data is replicated several times, so you don't have to worry about a disk crashing and losing your only copy of the data. Now, whenever you have a new platform, you ask yourself, do I have to learn yet another API? And with Windows Azure Storage, the answer is no. You use your standard ADO.NET Data Services that you're already familiar with. You can program using either .NET classes and LINQ, or you can use REST. And with that, you can use any platform and any language. So for the rest of the talk, this will be our agenda. We'll first describe the data model that Windows Azure Tables use. Then we'll have a demo which builds a microblogging application, and we will do this in two parts. Then we'll show the basic operations that you need to do over tables. This will use both .NET and REST. And finally, we'll display some advanced features of Windows Azure Tables. So what is the data model? When you think about Windows Azure Tables, you think about accounts, tables, entities, and properties. Before you can access any of the structured storage, you have to create an account. So you go to www.azure.com, and you sign up for an account. Once you have created an account, you can create as many tables as you want. And the nice thing is the tables are scoped by the account. So if that means that I can create a table called customers, and you can create a table called customers, and we could have our data entirely separate. So none of us reserves the name customers, which happens to be very common. Now, the table contains a set of entities, and the entity contains a set of properties. We'll go into this in greater detail. Now, the key thing you have to think about when you're dealing with cloud tables that you didn't have to think about earlier is the problem of partitioning. To enable massive scale, your table data has to be enabled for partitioning. So what is partitioning? So let's look at an example table. This is a table which maintains a set of documents, and in particular, it stores all versions of a given document. So let's define a partition as all versions of an example of a document. So if we choose the document name as a partition key, then we end up with two partitions. So we have one partition which contains all the versions of the examples document, and another partition which contains all the versions of the frequently asked questions document. Now, the nice thing about this is that the application controls what the granularity of the partition is. So you get to choose how do you want to determine how many entities should be in a single partition. Now, why is partitioning important? Now, partitioning is important because it has a significant impact on performance and scalability. So how does it impact performance? Now, this relates very much to the way you think about your standard database application. If you use a property that is common if you have a property that is common in all your queries, you probably would have much faster queries if it were a key property than if it were a non-key property. So one of the key things you should know for picking a partition key is that it's a property that is common in all your queries, and it should be a key property. So this ensures that all entities with the same partition key value are clustered. So in the earlier example, we found that all entities of a single document, so all versions of a single document would be clustered. Now, what about scalability? Now, partitioning is the unit by which we scale. So the Windows Azure Table servers monitor all traffic to the entities, and we automatically load balance partitions. So in particular, each partition could potentially be served by a different storage node. And this means that we can scale effectively to meet the traffic needs of your application. So for example, if document A and document N are very hot, we could put them on 2 different servers. And so the hot traffic goes to 2 different nodes, rather than both ending up on the same node. And from an application design perspective, the more partitions your table has, the easier it is for the servers to balance the load evenly across our servers. So let's look at the impact of entity locality. This should be very familiar to all of us who have accessed databases. So again, we have our example table, which has 2 partitions, the examples doc and the frequently asked questions doc. Getting all versions of the frequently asked questions is really fast. And this is obvious, because we're using the partition key to filter our query, and we're accessing a single partition. So this is the way a typical query would execute. It would find the first entity, the second entity, and the third entity. And now we know we are done. Because we're accessing a key property, we know when we can stop. On the other hand, if you have to get all the documents before 5/30/2008, this you can expect to be very expensive. A, it has to scan all the entities in the table, and has to traverse all the partitions. So the typical execution sequence would probably be like this. So you look at the first entity, it doesn't match. The next one doesn't match. The third one matches. But you can't stop. You still have to keep going forward until you hit the end of the table, and that is when you can stop. So as you can see, this can be a very expensive query. So in using cloud tables, you would choose your query so that they access the partition key primarily and do additional filters after that. OK, so we've spoken about partitioning and so on. What does an entity look like? An entity is the unit of data that you store. An entity can have up to 255 properties. These include 2 fixed key properties. So it means that any schema that you have should have 2 properties called partition key and row key. And these have to be strings. There is no fixed schema for the rest of the properties. So that means that 2 entities in the same table could have entirely different properties. You can think of this as flexible schema. And this might be a very convenient feature for your app. The properties are saved as name type value pairs. So it means that you actually preserve your type information and your names from between your client server sessions. So but very often you want your applications to work with a fixed schema. Now that is possible, but the application is responsible for enforcing that the schema is fixed. So your application should work in such a way that all the entities you create have the same schema. And that will ensure that all the entities you receive will have the schema that you expect. An entity also has a system-maintained version. This is important when we talk about concurrent updates later. The property types in particular can be fairly rich. As I mentioned, the partition key and row key have to be strings. Now, this has an impact on how you choose your key properties for your application. And Pablo will show some of how you handle that particular situation. The other properties are the set of rich primitive types that you normally expect in a database application. I will now hand it over to Pablo, who will start building the microblogging application.
Thanks, Nilan.
Thanks.
Thank you. So we were trying to find an example that was small enough that we can build here on stage, and at the same time, let us run into the typical issues that you will have to think about when building an application based on Azure tables. So imagine a microblogging application. The simplest one you can think of, it would be something where you post messages, and those messages go to channels. So there's a number of channels. And then users can follow those channels, can subscribe to the channels, and you can see what messages are being posted to them. And excuse me, an hypothetical homepage for this will be something where when you log in, in your profile, we know which channels you follow, and we will go fetch the latest messages for those channels and put them on the screen. Now, what is the trick here? The trick is, we always said, yeah, I have this idea, I'm going to build this website, and it's going to skyrocket, and everything is going to be good, and we're going to be all happy. So what happens when that happens? Like, this is initially, that sounds great until you actually hit it off with one of these websites, and now you have to scale the system. So what are the scalability challenges, even in a small application like this? First, you need to be able to take on a very large volume of messages coming into the system every day. Second, you need to be able to very quickly retrieve recent messages. So by recent, we're saying there is some criteria for hot data that needs to be retrieved very often and very efficiently. At the same time, you will have a continuously growing amount of data that is going to be coming into your system, and you'll very probably want to store this data long term. For example, you may want the messages in this microblogging application to be addressable and have a URL that is there for a long time. So let's go ahead and build an application like this where there is channels, there is messages, and you can think about a user profile that knows what channels a given user follows. I'll simplify that part a little bit. And the clicker doesn't quite want to do it, so I'm going to go like this. So let me go find here. So here I am in Visual Studio 2008, SP1. And all I did is I have VS and I have the Windows Azure SDK, so we can use some parts of the SDK to build the application. So what I'll do is I'm going to create a website for this example. I'll create a new project. And I'm going to choose, I will use the new model view controller, the MVC framework for this. And I'm going to call this application micro. Not a very creative type. So we're not going to write test on stage for now. And let's get the application going. So in this first part of the demo, I want to do three things. First, I want to define the data model or basically the data elements that my application will deal with. Second, I want to create in the table service all of the tables that my application requires. And third, I want to create a very simple web homepage that lists all of the channels in the service. In the second part of the demo, we will get fancier. So this thing should be created. So now we can create our actual application. You know how the model view controller deal goes is you have a model that represents your data. And for that, we're going to use .NET objects. You have a controller that introduces behavior. And it's the thing that actually gets called when you need to take action on a given resource or a response to a request. And then views are the thing that render the responses on the user. In this case, we're going to render HTML. So first thing we need to do then is let's create the data model for this application. And for that, I'm going to use simply .NET classes. So folks familiar with LINQ in general? Yes, a lot of you, great. So we're going to follow a very similar pattern where we have classes that represent our entities. So we'll have a class per entity, and then we'll have this Uber class that represents my entry point into the store. And we follow a pattern. Some of these things could be auto-generated, but in principle, there is a pattern that if you follow it, some of these things are going to be easier to do. So let me choose class, and I'm going to say here microdata. So we said we will have, I'll get back to this later. We said we'll create a few classes, and that in order to do that, we'll depend on the SDK. So I already have the SDK installed. So let me copy the path. And what I want to do is I will add to my project one of the SDK examples that actually comes in source code form. So I'll actually add the project to mine. And this sample contains a number of helper functions that will make your life substantially simpler when it comes to authentication and a few other details that you need to deal with when operating against the table service. So now I'll go to my project and add a reference to that guy so we can use it from our application. There. Projects, storage client. And there is the interesting namespace here is Microsoft.samples.servicehosting.storage client. I know we could have done better there. So now let's define the first class. This is the channel class. What is the channel? So I'm going to say public class channel. And as Niranjan mentioned before, every entity has at least a partition key and a row key. And you have to give meaning to these things. So in the case of a channel, I'm going to say that the partition key is the name of the channel. This is not great for clustering, but for the time being, it's going to do. Later on, we will talk about actually doing some partitioning. So I'm going to declare this as public string partition key and give it a getter and a setter. Whoops. And there. Then I'll put a row key into, which is the second thing that all of the entities need to have. And I'll put a comment here to remember that this is the channel name. So then I can add any properties I want there for my own use. For example, I'm going to add a datetime property called date created, so we know when the channel was first created. So structurally, now this class is ready to go. One thing I need to do is, since I'm using the AD.NET Data Services client to access this system, I need to tell the services client what are the keys for this particular object. So let me add a second reference to system, whoops, the data.services.client. And this is the standard client that actually comes with the .NET framework in the SP1 release. And let me add a using here to system data common, actually services common, there. So I'm going to tell the system now that this guy has as key the partition key and the row key. Since the client works against any service, it doesn't actually know that these two are the keys. So the last thing we may want to do here is give us a couple of constructors to make things easy to manage. So let's do a default constructor that our infrastructure requires, and then let's use a constructor that we use to create new channels, where I'll take the name of the channel, and I'll say here date created is datetime.utc now, and the partition key is the name of the channel. And then in this case in particular, the name of the channel is enough to uniquely identify this particular channel. So I'm going to say the row key to string.empty. So effectively, every channel becomes a partition. So this is a fully ready to go class now. We can use this against the table storage. So we need a second class for message. And to avoid getting everybody falling asleep, what I'll do is I'll actually grab one from here that is ready to go. This is the message class, and it follows the same pattern where I have the partition key. For the time being, the partition key is the channel name. We'll do better later. And then in the row key, what I'm putting is the date time of the creation of this particular message. And then I have a few elements here, like the text of the message, the author, the channel, the date it was posted, and the rating. And you can see I can just use CLR types, and we'll pick the right types for storage. And then we have a constructor here. So last step that I need to do here is, in principle, I could use this as is. These classes are enough to operate against the system. Now, I mentioned before this pattern that if you follow, a number of things become easier. This pattern is you create this class that represents your entry point into the system, and my microdata class is going to be that class. In a typical data services client application, this class will inherit from data service context, for those of you that are familiar with data services or Astoria. In the SDK, we have a subtype of that actually includes a number of utilities. In particular, it fully solves the authentication problem. So I'm going to inherit from that, and that is in the table service data service context. Table storage data service context. So I don't need to add a lot of customization. That will do most of the things for me. In particular, one of the things that it will do is, by default, it will go and read the configuration information to know what is my account for the table service and what is my endpoint and my private key. So I'll just put that information in my config file, and this class will pick it up automatically, so I don't have to do anything in my code. So let's open web.config here. There. And here in app settings, let me go. So I already got my credentials. I went to the Azure website, and I got them. And this includes the endpoint, the account name, and the share key. We debated what was the safest method to hide my key, because I'm not supposed to share it. And the high-tech solution was to put a bunch of spaces after it, but so far it's been working pretty well. So you can't see it, but I can assure you that if you go a lot to the right, or whatever. There is a key there.
I don't believe it.
Sure, sure. You want those keys, and we'll talk about that later. So last step. Now I want to finish this pattern by introducing entry points to each one of my tables. So we'll follow the link way of doing things, and I'm going to say each entry point is an iQueryable of the type I just defined. So I'll say my iQueryable of channel. The message is called, the table is called channels. And in the getter, I need to create the root of a link query. And then this will help us use link queries against the service. So I'll say this dot create query of channel against the table's channels. So by following this pattern, I hide this information here. And now everywhere else in my application, I just go dot channels, and there are no quotes or anything around. So I also have this message type, so I'll do the same thing with message. I'll put message here, copy messages here, and then here, message and messages. All right. So we're set up with the first phase. We defined our data model. We have messages, and we have channels, and we have this class that represents the whole thing. Second step, we need to create these tables in the table service. There is a couple of ways you can do this. Tables are actually held in the tables collection. So there is actually a table that contains the tables. So you can simply go to that table and create an entity which is a table, or remove it, or list them, and so on. So that's one option. You can do maybe a program on the side that does this once during initialization or something. Another option is during your application initialization, you can check if the tables are there, and if they are not there, you can go create them. So I'm going to do that. Since I follow the pattern, I actually can simplify this further by saying I have this class that represents my entry point. Go look at the class. Those are the tables I want. Just do whatever you need to do so I can just run my app. I don't want to think about the tables. So let's do one of those. So I'll add the same namespace I used before. There's Microsoft, that samples, that all that. And here, what I'll say is tables dot create tables from model. And what I need to do is pass my model class. So this is type of models dot microdata. So there you go. That's it. When you call this guy, we will go look in the table service. If any of the tables that are represented, let me switch back, by these guys, these properties, if they are missing, we'll just go create them on demand. So third and last step is I want to write the home page such that it lists all of the channels. We'll do more later, but for now, let's just list the channels. So I need to do this in 2 steps. First step, I need to create or actually change the controller so that the homepage controller queries all of the channels and breaks them into a data structure in memory or something. Second step is the view has to pick up that information and render it on the screen. So let's do the controller first. So in the controller, the index action or method is the one that gets called on by default on the homepage. So what I want to do here is I'll remove these guys. What I want to do here is I'm going to talk to a table service. So I'm going to create a new models.microdata, which is what I use every time I want to hit the service. And now I need to populate the list of channels. And what I'll do is I'll say view data, which is the bucket where you put the stuff that the view will render. And I'll say channels equals service.channels. And I already gave myself a property for this, so that is enough. I could write a link query, and we will talk about queries in the second part of the demo. So at this point, I'm done with the controller. So let's finish this off by creating a view. And that's not a view here. So in the share part, we will change maybe just the title to call this PDC micro demo. And in the homepage, what do we want to do here? Simply iterate over all of the channels and print them in the screen. So let's go do that. So I'm going to say this is the list of channels. And the first time I'll do it all by hand so you can see all the steps. The next iterations will actually go and reuse some stuff. So what I want here is a list. And inside the list, I want to for each the channel, and say for each channel in. And what was this? This was an enumeration of the channel type. So I'll say IEnumerable of models. Actually, I think I need to say the whole thing, micro.models.channel. And this was view data and the name of the bucket was channels. OK, there, for each. And then at the end is for each. Let me just close this before I forget. So what do we do here? We put a line item, and the line item is going to say channel dot. Remember that the name of the channel was the partition key. So I'll say partition key. And then maybe in parentheses here, we'll say channel dot date created. Go like this. So I already pre-created the channels table and put a few channels in it, so we can actually see something when we run this application. We'll talk about creating new entities in the second part of the demo again. So finally, let's run this thing. Let's see if it actually runs. Maybe I should set expectations. It's not going to be impressive. It's a list of channels. Let's see. But the whole cloud thing is going on. Like you will go to the cloud, grab the channels, come back, and here's the list of channels. So very simple, but it highlights. Thank you. Thanks. So very simple, but it highlights the main elements of the flow. Get the SDK, get into Visual Studio, create the model using your classes, create or set up some mechanism to create the tables. Third, just access it using regular .NET objects, and in this case, an ASP.NET application. With that, I'll give it back to Niranjan.
OK, thanks, Pablo. OK, so Pablo just showed you how easy it was to get started programming Windows Azure tables. So let's reinforce what we saw, and let's look at what happens under the covers a little more. So Pablo created the channels class and copied the message class. So let's see how the message class is built. So as Pablo mentioned, to define the schema for a class, you simply have to build the C# type for that class. Let's step back a little bit, actually. So when you build a standard database application, what are the steps you normally do? You build your model, so you get what your schema for your application is. Then you create your tables. Then you insert your objects. And then you probably update, query, or delete your objects. So we'll do exactly the same things step by step. So to define the schema as a .NET class, start off defining the C# class. Add your fixed properties. Let me just use this. So the fixed properties, as we mentioned, have to be partition key and row key. And since we have fixed the names that you have to use for these keys, you will almost always have a comment which says, what does this actually represent? So for the message type, it represents the channel name for the partition key and the posted date for the row key. Next, you add all the remaining user-defined properties. And as you can see, these properties are quite rich. You can use a string, an integer, and you could use any other thing, for example. Finally, to make it work with ADO.NET Data Services, you apply the data service key attribute. This attribute says, given a certain entity, which properties make it unique. Now, I mentioned that we have two key properties. Why do we have two? Why couldn't you have just had one? Right? So the reason for that is to be able to separate the notion of how you partition your data from what makes an entity unique. Right? These are two separate things. If you had only one key value, and that was the only thing you would use for partitioning, then you would effectively end up with all partitioning being exactly one entity's large. And that is obviously not suitable for most applications. So by having two separate properties, your application gets the best of both worlds. You get to have almost full control over what makes your entity unique, but you still get to tell Windows Azure's table how the data should be partitioned. So now that we have defined the schema, the thing about the schema is it is a client-side piece of information. You don't actually tell the server what the schema is. So primarily use schema to make sure that your application is self-consistent, as it were. So let's move on to see how it is used. Let's insert an entity that is a new message, which happens to be relevant to today. So to create a new message, it involves a few basic steps. As we told you, it was very convenient to program this in C#. So you first create a C# object, as you've done now, set all the properties. So this type had 4 properties, and you set the value for each of them. Next, anytime you use ADO.NET Data Services, you have to create this data service context. If you've used many SQL APIs, you can think of this as representing the connection to the Windows Azure table servers. So when you create a data service context, you have to specify the URI for the service. And why do I mention this URI? Throughout this talk, you'll have to remember 3 different URIs. The first URI that you see is the one I'm showing you now, which is the service URI. The service URI looks like your account name. That's the account name you created in Azure.com. And then you have a fixed part that follows it. You have the keyword table, which says that you're accessing the table service of Windows Azure Storage. And then you have core.windows.net, which represents the base domain for all of the Windows Azure Storage services. Now that you've created this data service context, you call the appropriate methods on the data service context. So to create a new object, you call the add object method, very intuitively named. And when you do this, you specify the table name that you want to use. In this case, it happens to be messages. And you specify the C# object that you created. Finally, you call the save changes method on the context. It is at this point that an HTTP request is sent to the server. So what happens under the covers? Under the covers, this is what happens. It's the same as sending a REST request to the Windows Azure table servers. So first, you send a post message to a specific URI. Now, this is the second of the important URIs that I mentioned. This is a URI for a specific table resource. So the URI for a table resource is a service URI that I spoke about earlier, and to that you append the table name. So that's how you get the URI for any table. And once you have the URI, you can specify the rest of the body as in an XML format. So here a bit of detail would be interesting. So under the covers, ADO.NET Data Services uses the Atom Pub protocol to exchange data between the client and the server. So if you look at this, this would look very much like an Atom feed that you're already familiar with. And you can see that the values are exactly the same as we had in our C# in our .NET application. So when this request is sent to the server, an actual entity is created on the server, and you get success back. So let's do a few more things with this message. OK, I skipped very rapidly over a very important step. I didn't create the table first, which Pablo very regularly did. Now, why didn't I do it first? Because creating a table is really the same as creating any other entity. It is really just an entity in a special table called tables. So every account has a table called tables, which stores a list of all the tables that it has created. Well, I'm probably going to be saying tables too many times. Well, anyway, the schema for this table has exactly one property called the name of the table. And here's where you want to remember the important statement that I made before. This has just the name of the table, not the schema. So schema is known only the client app, makes your client very easy to write, very easy to get correct. But on the server side, all that is remembered is the name for the whole table, and all the types and values are stored in the actual entity themselves. And you get the great benefit of flexible entities with that. So you repeat the same steps that we did for create entity. You create your data service context with exactly the same service URI. You create your C# object with the name of the table you're going to create. You call the add object API, and you're adding this object to a special table called tables. And you call save changes, and your table has been created. So great. So we have created a table. We have created at least one entity in this table. Let's do the rest of the things that you normally do with an entity, which is querying, updating, and deleting. So querying is really nice. So if you're already familiar with LINQ and C#, you already know how to query a Windows Azure table. So you get the full power of LINQ and the simplicity and everything that goes along with it. So how do you query? How do you do an actual query? As always, you create your data service context. You start off with a query that represents all entities in your table. So this you recognize as a standard pattern for representing all entities in a table. You apply your filter. If you remember, we created one entity, one message, and we set the rating to 3. So that's why I have a filter which is chosen as such. Now, so far, you've just defined your query. To actually execute your query, you have to enumerate it. So the nice thing about this is you can actually save multiple queries, and you can save them off for execution later. So the execution happens only when you enumerate it, for example, when you call the for each statement. And what happens under the covers? In the REST, it translates to a get message, where you use the URI for the table, and to that, you append a $filter equals rating equals 3. And you can see that this URI is really simple. It is very similar to the link that we just typed in the other place. So even if you had to create these URLs by hand, for example, in any open or HTTP stack-based solution, it will be very easy to do so. And when this is actually executed, what happens? So the request is sent to the Windows Azure table servers. The server processes the request, and it sends a response back as an Atom Pub feed. On the client side, ADO.NET Data Services deserializes Atom feed, deserializes the XML, and converts each of those XML fragments into a C# object. So now your client is really easy. You can just work with the message objects in C#. No XML if you don't want. OK, great. So we've queried our entities. Let's go into updating the single entity that we got. To update an entity, you follow a few basic steps. You fetch the object in the client, and you do that, as always, by executing a link query. And in this particular case, you write your query so that you get a single entity back. And how do you get a single entity back? You execute a query which has all the key values set. So if you remember, our partition key was channel 9, and our row key was October 29th. So if you specify both of these conditions in your link query, you would end up with just one object back. So we are very safe calling first or default, and we are sure we'll get one value back because we know it is there. Now, when you execute this query, what happens is the actual object is materialized at the client application. So you have a client object, and to start off the update, you just update the C# property. So here we're changing the text of that message from hello PDC to hi there. Now, even though you're changing the object in memory, ADO.NET Data Services does not know that the object has changed until you call the update object API. So by calling the update object API, you're registering in the context saying that this object has changed. So when you finally call save changes, ADO.NET Data Services knows how to send the right request to server to update exactly the right set of objects. And what does it look like under the covers? You have a put request. And here, we come to the third special URI that we saw. The special URI is a URI for an entire entity. So the URI for an entire entity consists of the service URI, followed by the message, the table name, which was the URI for the table, and you follow that by the key columns. And in the body, it is again an atom feed, where you specify the full XML. For simplicity, I've just shown the part we have changed, but in general, you'll have all the values for all the properties. Now, the ADO.NET Client Services Client Library supports two kinds of updates. You can either update just a part of an object, so you can leave all the other parts unchanged, or you can replace the entire object. I do not show both of them, but the API allows that. Deleting an entity is almost as easy as updating an entity. You fetch the object, you call the delete object API instead of update object, and you call save changes. And when you do this, under the covers, you send a delete request to the server with the URI for the entity. So what have we said so far? We've said that you can program on either .NET using ADO.NET Data Services, or you can program using REST. And the reason that you would get exactly the same behavior in both cases is that the ADO.NET Data Services, under the covers, is built on top of the REST API. So you get exactly the same behavior whether you're doing it in .NET or in REST. So let's summarize what we saw. You can write your applications using either .NET or REST. So in one case, you would use a client which ships with .NET 3.5 SP1. So if you want to use no additional code, you can do it. If you're using with any platform and any program, you can use any HTTP stack. You could work either with data as .NET objects, which is really convenient. You have your IntelliSense, you have your type checking and all those things. Or you can work with data which is represented in Atom or XML. So that will work with your standard AJAX toolkits and other such things. To update your objects, you could either use methods in the data service context, which is add object, update object, or delete object. Or you could use the standard HTTP verbs, which is put, delete, get, etc. And to define your queries, you can either use LINQ to define your queries in .NET. So you get almost a SQL-like language interface if you're already comfortable with that. And if you want to do it with URLs, you can use URLs to define your queries. And as we noticed, the URLs look really clean. They look almost like the link that you used to generate that were corresponding to them. Great. So now I'll hand it over to Pablo to finish the demo on the microblogging application.
Right. Thanks, Niranjan. Is that my app? Oh, this one. Oh, there. All right, so let's finish this application. I want to do 3 more things now. First, I want to take the data model that we have and tweak it so that it's actually partitioning friendly. Second, I want to add a way to create new messages in the user interface and post the messages to the table store. And third, we want a more sophisticated homepage that can actually list the messages that are posted and maybe filter them by channels and by users and so on. So let's get started with the first part. Let's teach this thing to do partitioning well. Let me switch back to Visual Studio. And I need to go to my data classes here. So let's focus on message for a second. So let's say, again, we hit it off. Our volume in the website is skyrocketing. Now we have this crazy amount of messages, and we want the system to scale. What do we do? So initially, we said, well, the partition key will be the channel. Is that a good idea for partitioning? Well, not quite, right? Because if you think about this, we will pile over time a lot of messages in a partition. So even in a channel, rather. So even if we had a lot of channels, we'll still, a particular channel, the partition that backs the channel, will still keep growing over time. And that will have a mix of hot data, which are recent messages, and cold data, which are messages from very long ago. So that doesn't seem quite like a great strategy. So we're going to tweak this strategy as follows. We will go under the argument that the important, or the hot data rather, is data that is per channel, per time frame. And let's pick a day as a time frame. So what I want to say is, when you walk into the home page, I want to give, for the channels that you follow, I want to give the messages for that channel for that day. And I want that to be fast. So by fragmenting by channel and by date, now we create these relatively small buckets that contain only the messages that went to a particular channel to a particular date. And as the volume of the data grows over time, what we have is many different channels across the table service, which are partitions again, and each one of them of a manageable size. This also lets you choose the granularity of the partition. I'm going to use day for the time being, but if the volume keeps growing, you can say, no, actually, I'm going to partition by channel, by hour, or by minute, or whatever is appropriate for your context. So let's change the message class for this. No, we're not going to make a lot of changes. The main change is the partition key right now is only the channel. What I'll do here is I'll add a quick function here that we're going to use in a couple of places that says make key. That's going to take the channel name and the date time that I want to use. And the partition keys are just a string, no particular format. So I'll just cook up a format. I'll say I'm going to use the channel name and then the @ symbol. And then I want the granularity of a day. So what I'll do is I'll to-string this date. And I'll say use the year, followed by the month, followed by the date. And drop the hour. So basically, what we're doing is we're grouping together all of the messages, same channel, same day. Now, I'm going to change the partition key of the message to be make key of our target channel and this .date posted, which is the date this particular message was created. So with that small tweak, now I'm going to get this sort of partitioning or grouping of messages that will allow later on to do efficient query when rendering the home page with my hot data. OK, so we're done with first step. Second step, we need to teach the application to create new messages against a given channel. So let's do that part. In order to create messages, I need to create the UI, and then I need to create or augment the controller to handle the UI element. So let's do the UI stuff first. I already have a form prepared here. So let me copy-paste this guy, and I'll walk through it. I'll say this is H2 post message. And here's our form. The form posts against the post message action, which I need to go write in a second. And it has 3 fields: the author, the channel, and the message. And you can imagine doing this more sophisticated by being logged in, and the author is you and all that stuff. But for the time being, this will do. So now let's write a controller that takes this information and creates an entity of type message in the table service. So back to the controller. And in the controller, I'm going to define a new action called post message. And again, the members of the form were the channel, the author, and the message text. I'll also mark this thing as accepting post verbs, since I want to use it for a form post. All right. So what steps we need to go do here? First is I'm going to need my entry point to my table service. So I'll create one of these thingies. Remember, this also deals with all the configuration goo, so you don't have to worry about it here. And now, first, let's check and make sure that the channel exists. So we'll write a quick query here that says from, and I'll write a link query, from C in service.channels, where C.partition key, remember the partition key is the channel name, so I can just say channel, select C. And now, if I want to check if the channel exists, I can say if first or default of this guy. If this returns null, sorry, if this does not return null, does return null, come on. If it returns null, it means that the channel does not exist and we want to fail the request. So I'm sure you can do much better in the UI department. My fancy way of telling the user that he didn't do well is I'll just say invalid, or actually argument exception, and we'll say invalid channel. This is the part where you put an actual UI here to be all nice to your customer. So now we know the channel exists. Let's go create the message. So I'll go message equals new message, actually models.message. And we already have a constructor that is very convenient. Let's use that guy. We'll put the channel, the author, and the actual message text. So as Niranjan said before, now we have to tell the context object that we have a new message to be added. So I'll say service.addObject to the messages table, use the object m. And finally, I want to push all of the changes into the table service. I could pile up a number of changes here and then call save changes, and we'll send one by one together to the table service again. So I'll say save changes, and at this point, everything is down in the table service, and I can actually re-render. In this case, I'll just re-render the home page. So I'll say return this redirect to action index, which will do the trick of re-rendering the home page. So this is not very interesting if we cannot see the messages, so let's tweak the initial controller to actually pull the messages and put them on the screen. I'll do this kind of in a simple fashion, and then I'll do a more sophisticated round. The first one is I'll say in the viewData.message, I'll put all of them. Of course, if you really have all of this multi-billion number of messages, this may not be a great idea, but we'll do it here, and then I'll change it. And in the view, now I want to list all of the messages, and for that, I already have a snippet here, because it's very similar to the one I did for channels, so there is not a lot of value in me typing all of the stuff again. So I'll just put it there. And I need to say here micro. Whoops. There. So this should do. So let's run this application, see what happens. So here's my new app. Now I have this little form here, and let's create a message from Pablo on the channel. Let's do a bad channel first, bad channel. Foo, hit send. So we go query the table service, don't find a channel, so we throw an exception saying invalid channel. Let's put a good channel here, 2008, and something like what a great event. Click send, and now we have the message right here, so we created a new message. And I can keep going. Let's create another message from Pablo in the sports comment, some sport comment. I actually don't know much about sports, so whatever. Actually, let me do a third one so I can filter stuff later. So we'll do one by Niranjan in PDC 2008 saying, please be done with your demo already. And so now we have 3 messages. And we're creating them in the table service and then re-rendering the UI. So let me go back to the code. What I want to do now is this home page is not going to fly because of what I talked before. Like we have just too many messages. So what I need to do here is retrieve messages that make sense for a particular home page. So the simplification we will do is, instead of having a user profile and all that, we'll take a channel in the query string and we'll render the entities, the message entities for that channel for the day of today, which is what you would do in the real application. And that will leverage the partitioning scheme. So let me go to the controller and say, we'll take an argument here that is the channel. And then here, actually, let me go here and say, I have a query that says from m in service.messages, where m.partition_key equals, and remember that the partition key without the row key is not unique. What it does is it retrieves a whole bucket of information. So here, I'll use the function I created before in message called makeKey, where I'll pass the channel and datetime.utc now, and then select m. So what this query does, let me put the query here, is effectively selects a single partition. You're guaranteed that this query is not going to span partitions. So it should be fast, quote unquote, in that sense. Before I go, so I'm going to run this and you'll see a subset, so I don't want to iterate over that. Let me do one more thing and then we'll be done with the whole application. So far we created all of the queries that we've created are on partition keys. You can also query on arbitrary properties, and we're not going to do as fast because they are not indexed, but they work. And you can also combine the two and maybe further filter the messages in a particular channel in this example. So let's do that. So let's say that optionally, you may give us a name. And if you give us a name, you only want the messages for that name. One of the nice things of LINQ is that you get query composability, and our URL, so LINQ to URL translator actually deals with this just fine. So what I'm going to do here is if not string that is null or empty name, so we were given a name. So let's augment the query with a second filter. And what I'll do is I'll actually query over my query. Since we do deferred execution, this composition will go just fine. So I'm going to say from m in the query I defined before, where m.author equals the name I was given as a parameter, select m. And then finally, I'll just bind this to the UI as I do here. So what this means is, let me run this thing again. Now we get to see messages on a channel or on a channel by a particular author. So let's go to the UI. And we don't see any messages because I didn't say any channels. So I'll say channel equals PDC 2008. And you can see there's a couple of messages here, one from me, one from Niranjan. And if I then here say name equals Niranjan, here is Niranjan screaming that I finished this demo. So you can get both sides of the query side. Thank you. Last thing I'll do before I give up and run away is let me attach a debugger to this thing. I want to highlight a couple of things. So Niranjan explained before how we actually take all of these LINQ expressions and we just translate them to URLs. So you can do the same thing from any other environment. So I thought I would just quickly show that. So let me come here and say channel equals PDC 2008. That was weird, wasn't it? Let's try again. Oh, there. That looks more promising. There. So let me hit F5 actually and put the whole thing here. So I'm going to say channel and name. So we hit this first part. This is not empty, so we'll further compose the query. And if I take this query and put it on a watch, and let me try to do this so you can actually see it. There. So you can see that the query is actually /messages and then question mark filter. So it's just a URL query that we generated based on the information you gave us in the LINQ query. And even composition and all that was sort of dealt with automatically for you. So last thought about this, so now here we have a small application working. Last thought about this is a user may actually have, in a more real application, multiple channels that you're following. So if you want to retrieve messages from these channels, sure, you can give it to the system, but as a single query with a bunch of ORs. But you can also leverage the fact that the table service itself is a massively parallel system. So what you can do is use the async APIs in data services to fire off, say, the whole 10 or whatever queries you have at the same time. It's not like you're going to slow down the table system. The table system will just take it. And that way, instead of serializing the cost of composing the homepage, what you get is only the cost of the longest, of the sort of slowest of the queries. So it's an easy way of getting very nice parallelism during your execution. And with that, actually, I need to do one more slide on this side of things. Thanks. So a couple of highlights that I wanted to do before wrapping up and returning control to Niranjan is, so what you just saw me doing in Visual Studio was just Visual Studio. Like, there weren't a lot of weird things there. Just VS, .NET classes, LINQ queries, data services client. So one of the things we worked a lot on is on making sure that you can transfer your .NET skills as is to the cloud. This application not only is using the table service, but the same app, I was running on my computer, but it could be running on the web. Like maybe the app itself is running on the hosting service. And you're still just writing an app just like, almost like you would do any other day. So very high level of portability of skills. So we're also fully compatible with data services, which means you get to reuse the data service client, you get the LINQ translator and all that good stuff for free. And also, we have a bunch of integration points with ASP.NET that you can leverage, including a data source control that you can use. You know, I used MVC, but you can, of course, use regular, like traditional ASP.NET with a web forms framework, and you can use the data source control for data binding. We also have dynamic data support. So if you like dynamic data, you can type your classes and then point dynamic data to it, and bang, you have a website hitting the table service. And also, in the SDK, and this is very nice, so the SDK team built ASP.NET providers. Those of you that are familiar with them, they give you instant support for roles, for authentication, like profiles, and a number of other things. And you can remove the SQL Server ones that you were using when you are on-premises, and then swap them for the table service ones, and maybe you're running entirely hosted, and now you automatically get the same services you got on-premises, but now on the cloud. So a lot of opportunity to transfer skills and still build great applications. With that, I'll give it back to Niranja.
Thank you, Pablo.
Thank you.
So far, we've been telling you that the simple things are simple. So for standard inserts, queries, updates, and deletes, you can reuse everything that you already know, and you can build these great, rich applications. Now let's look at some of the advanced features of Windows Azure Tables, some of the things where you have to think slightly differently from the way you did in the past. So there are 3 topics we'll touch upon. How do you deal with concurrent updates? How do you deal with pagination of a large number of results? And how do you deal with consistency across tables? So if you recall how we did the update of a single message, we did 3 steps. We first fetch the message from the server in the client. We update a client-side C# object, and then we send the object back to the server. Now, as you can very well imagine, after the time you fetch the object in the client, somebody could have changed the object in the server. Now, you don't really want your update to apply after that point, because you will be losing somebody else's updates. So you want to be aware of that and handle it appropriately. So let's see what happens. So the mechanism we use is built on top of standard HTTP mechanisms. So in particular, it's the e-tag, which tells you what version a given entity is at, and the if match, which allows the client to tell the server what version it thinks it's updating. Okay. So we're trying to, both clients A and B are trying to update the entity in the middle, which is channel 9 created on January 2nd. We have the version on the left-hand side of the entity and the rating on the right-hand side. So both client A and client B get the entity. So client A gets the entity. It says the version is 1, and the rest of the entity is the same. Client B gets the same value. Client B, both of them change the entities locally. So client A changes it to 5, and client B changes it to 4. Now client A sends its update to the server first. So it sets the update, which is a version check. And this is the request that goes to the server. So it sends an if match header, where it says the version it expected was 1, and this is the new values to replace the entity with. When the server sees this, it compares the if match version with the version on the current object. They match, so it accepts the request, and it's a success, and it updates the entity. And when it updates the entity, it updates the version and sends a modified e-tag back to the client. So client A now knows that the version of the object is 2. But client B still thinks the version is 1. So when client B sends its update, it sends the same if match header. The version is 1, but the server's version is 2. The server compares the 2. It says 1 is not equal to 2. So it says the request has failed, and sends a precondition failed or 412 error message back to the client. If you had written a .NET application, you would get a data service exception back at this point. And then the thing is, the fact that you get an exception back allows you to decide what kind of retry mechanism you want to have. So your typical retry mechanism in the presence of concurrent updates would be repeat the process. Fetch the object again, do your retry, update the object locally with the new value that you expect, send it back. You will eventually succeed, or you can fail after a certain number of tries. Now let's talk about pagination. So your messages, your application has become very successful, and you're getting hundreds of messages. But your UI really doesn't want to display 500 messages at a time. It probably wants to display only the top 100 messages. So how do you make that happen? So pagination consists of 2 important aspects. The first is the ability to get a small subset of rows or entities. And the second is the ability to continue a query from where you stopped. So let's look at the first part. How do you limit yourself to a subset of entities? So again, this is a standard link query. We start off with the same data context. We start off with a query which represents all entities in the messages table. And we reduce this by applying the standard link take function. So when you apply the take function to a query, it reduces the result set to the parameter they pass, which is 100 in this case. So when you execute the query, you'll get the first 100 results back. And what happens out of the covers? You should expect this by now. A REST query is sent to the server. You get the same URL that you use for the entire table, and you have a filter which says $top equals 100. And that gets exactly the same results. You get the 100 entities back. So now, how do you get the next 100 results? So that's the part where we come into pagination. So the Windows Azure table uses this notion of continuation tokens. And if you are familiar with the Atom protocol, they have these next and previous links, and this is modeled roughly after that. So you send the same request we sent earlier. So you have your service URI, and you're trying to get the top 100 results. So this is the table when you started. The results of this query are the following. You get the first 100 results of this table, which have dates from 1 through 100, and you have a pointer to the next query. That pointer is returned in the response headers. So as you can see, there are two response headers, the next partition key and the next row key. This, roughly speaking, points to a key, but you should treat it as an opaque object. In particular, this entity could be deleted and your continuation could still work. So what does the next query do? It starts off with the same query that it had in the beginning. So the same query which gives you 100 entities at a time. But in addition, it uses the information that it just got. It adds HTTP query fragments, which says next partition key equals channel 9, which is the value you got from the header. And next row key equals date 101, which is the row key you got from the header. And when you execute this query, the server will get you the next 100 results starting from date 101. So this is how you can make pagination. So this is a pattern you would use typically over and over again. You could need to paginate for a variety of reasons. One of the reasons which we've shown here is you have manually decided that you want only a certain number of entities back. You have said you wanted only 100, so the server stops after 100. There could be other reasons why the server gives you less than what you wanted. One is because your query executed for a very long time on the server. So if your query executes for more than 60 seconds, the server will stop the execution and return the partial results at that point. So you would still have to inspect the headers and decide whether you have to send a new query to get the additional results back. The server could also send you partial results if your data was very large. So let's say your entities are very large. You're storing images and many images in each entity. Server limits your response to 4 megabytes per response. So again, in each of these cases, your application should be aware that you might have more results and should keep checking the continuation headers until there is no more headers, and then you can stop. Finally, let's go into the issue of consistency. So Windows Azure tables provide ACID transactions on updates for a single entity, and that automatically means it's a single partition in a single table. So inserts, updates, and deletes are the standard ACID transactions that you expect. On the other hand, for queries, we have something called snapshot isolation within a single partition and a single query. So what does this mean? This means that the results you get back corresponds to the state of the server at the time your query started executing on the server. Right? So let's say you started at 10 o'clock and we ran for a minute. Then you get the state of the results at 10 o'clock. So any changes that happened in the minute that followed after that will not show up over here. So what does that mean? You see no dirty or uncommitted reads. So everything that goes on at the same time does not affect your query results. So the results you get back represent a committed state. So you can trust the results you get back. Finally, this does not block concurrent updates, which is one of the nice things you would expect. So that's great for the server, great for your application. While we do have snapshot isolation for a query, there is no snapshot isolation across partitions or across different continuations of a query. Now, as I pointed out, in the pagination example, you have to send multiple queries to get all the results that you wanted. So that meant you sent multiple queries to the server. Each of these queries would represent a different snapshot in time, because they all start at different times on the server. So you have to be aware of that possibility when you evaluate the results that you get back. OK, so we've been talking about a single table. But the microblogging application was a lot more interesting than that. It had two tables called channels and messages. And most realistic applications, we want to keep them in sync. So let's look at how we can possibly do that. When you're using Windows Azure tables, the application is responsible for maintaining consistency across tables. So in the microblogging example, one of the things you might want to do is when you delete a channel, you also want to delete all messages for that channel. And this touches two different tables. So how do you make this possible? Let's look at that with an example. So we have the two tables, channels and messages. We have a queue, and we have two front ends, and we have a worker. Now let's talk a little bit about the queue. Windows Azure provides lots of services. We've been talking about the table service for the past hour. But in addition, it supports blobs and queues. Now, queues are going to be very useful for ensuring that this cross-table consistency thing works. So what happens? You have two different front ends which receive messages to delete channels. So each of them queues entries into the queue. So if the first one says delete channel 1, another request says delete channel 11, and the third request says delete channel 5. The worker request polls this queue at periodic intervals, and it retrieves the first queue entry, which says dequeue channel 1. So worker 1 tries to delete the channel 1 operation as such. So what are the steps that are required? Delete the channel 1 entity from the channels table, and so there it's gone. Delete all the messages for channel 1 from the messages table. So we delete the first one, the second one, and the third one. So now we have deleted all the messages, and we are done. So we delete the queue entry, and it's done. OK, so where exactly do we use this queue? We put stuff in and we pull stuff out. So it's very important when you have failures. So let's say the worker 1 failed when it deleted the channel entry and some of the messages in the messages table. How do you ensure that this thing completes? You have no entry in the channels table saying there's garbage. So you have no way of continuing from that point on. So you need some other state which says, well, I still haven't finished that operation. And let's go into that. So what does worker 1 do? We repeat the same steps as before. It dequeues channel 1 and starts the delete. Now here, I have to mention one more property about Windows Azure queues. When you dequeue an entry from the queue, you can say how long you expect it to be invisible. So what does that mean? That means if you don't finish the operation within that time, let's say 30 seconds, and you haven't deleted that entry, somebody else can see that entry in the queue and restart the operation. And that's going to be very important, because when you fail, you don't tell anybody that you've failed. Somebody has to know that automatically. So what does worker 1 do? It deletes the channel 1 from the channels table, deletes a message 1 from the messages table, and it crashes. So it fails, it crashes, and it has no idea where that queue entry went. So 30 seconds later, let's say, the channel 1 entry becomes visible again in the queue. So it's back into the original state, except that you have some deleted messages in the two tables. So worker 2 now picks up the same request. So dequeues channel 1 and retries the whole operation, because it doesn't know where it stopped. So it tries to delete channel 1 from the channels table. That's already done, so there's nothing done over there. And it deletes each of the messages from the messages table. Message 1 has already been deleted, and the other two haven't been deleted, and now it's gone. So now, the second worker has successfully completed the operation, in spite of crashes in the first worker, in spite of partial work from the first worker. And so that's how, by using both Windows Azure queues and Windows Azure tables, you've managed to implement consistency across different tables in what you would think almost transactionally. OK, so we've spoken about how easy it is to work with what we have. What do we have in the future? At PDC, in the current CTP that we have, we use a single index for the tables. So if you query and retrieve results based on partition key and row key, they're very efficient, and your results are sorted by these values. In the future, we will have support for secondary indexes. So when you query or retrieve your results by other properties, they can be either more efficient, or you can get those results sorted by that value. Now, I have to remind you that you can still you can still filter across other properties at this point. It is just the efficiency that will improve in the future. About transactions, we currently support single entity transactions on the table server. So if you update, delete, or insert a single entity, that is atomic. But as we showed with the messages example, there are cases where you want to do multiple operations at the same time. So in the future, we will support this notion of entity groups. So we will support atomic transactions across multiple entities, but they have to be within the same partition. And again, this is trying to drive home the point that partitioning is one of the key features that enables scalability of table storage. So in summary, Windows Azure tables are massively scalable and highly available. And as you've seen over and over again, they have a very simple and familiar API. They're very convenient to use. You can either use .NET, and you get the full power of ADO.NET data services and Link. Or if you're used to programming in other platforms and environments, you can use REST. This allows you to leverage your existing .NET expertise, C#, Link, ASP.NET, the whole works. And finally, here are some resources. The Azure website, the ADO.NET data services will give you more information on how to use ADO.NET data services. And finally, there's a talk after this which talks about what are the best practices you should use in general when you're programming cloud storage. That is in the Petrie Hall at 3. Thank you. We are now open for questions.
Well, thank you. Before we go to questions, who's wearing one of these Azure bracelets? Whoa, a bunch of people. That guy over there. So you get a full loaded soon here. Wow. I had nothing to do with it. Some dude came and told me to do this. So thanks. All right, so now we're open to questions.
OK, you want to start?
So if you fire up a bunch of deletes in a RESTful, do you put those requests on a queue internally for us? Or do we have to manage that?
No. So if you want to use the queues, you're doing it explicitly. If you're just sending a standard bunch of delete requests, they all happen independently.
OK, so if we use ADO and such, we don't get the queuing.
Yes, you don't have to deal with queuing.
Got it. OK.
Question over there.
You want to go?
Okay, hi. What are the main differences between Azure Tables and SQL Data Services?
OK, so Azure Tables are designed for low cost and efficient and large scalability. SQL services will give you much richer functionality, which is, for example, joins and pretty much relational databases. So Windows Azure Tables is not a relational database. It's designed to provide scalable tables at low cost.
Hi.
OK, so there's somebody in the back. Okay,
if you want to query, I'm sorry.
Who's the?
If you want to query by, for example, the date created on the messages.
Yes.
Those are being, and you want to say between two dates.
Yes.
Say between Monday and Sunday, something like, or particular dates,
yes.
October 1st through October 7th.
Right.
Is it smart enough on the back end to only query those containers that are using that partition key because they're partitioned by date? Say if you've got 365 partitions because you've got a year's worth of messages that have been archived.
Right.
Or that have been partitioned. Is it only going to query those 7 containers that are between using a less than and a greater than on the link,
so
on the link query?
Right. So if the date happens to be your partition key, then we will have efficient queries even for ranges across dates.
I'm sorry.
One thing to highlight about that is, so you need to, for the queries that are important to you, you need to make sure that you craft your keys so they allow for those queries. So in the context of the example we just did, so first of all, as Niranjan said, if the partition key was itself a date and it was properly sorted, then the range query would be efficient. In the case of the example where the prefix is the channel, what you can do is you can craft your query carefully such that the range query includes both the channel prefix and the initial date and then the end date, because in the end, our range query is based on the string. And if you want to do this over multiple channels, you just issue the query multiple times, which each one of the channels. So you need to think about the partitioning scheme every time you go into the table service if you want to pick up an index.
Right. You want to go?
In your example, you started with the partition key being the channel name, and then later you changed it to the channel name plus the day.
Yes.
If you've done that after you've gone live and you've got live data, how do you deal with that situation? Can you rename the partition?
At this point, you have, at the CTP release, you'll have to reload your data so that you repartition your information.
That is, of course, if you want to repartition, right? If you're fine with having your old buckets being maybe larger and then having higher granularity in the new buckets, and your application understands that sometimes you will get shorter partition keys than other times, then you can actually do this incrementally. Remember that we know very little about the schema of your classes on the table server side. So if your application can deal with different kinds of keys and they don't clash, you don't need to do anything. Of course, if you want to rehash and repartition everything, then yes, you will have to reload your data.
So I have a question about the flexibility of the schema related to, let's take message for an example. So suppose you had different types of messages.
Right.
So the one message was a question message and another message was an answer message, and you wanted to define 2 classes to model those types. How is that compatible with the and the base class, of course, being message for these 2 derived classes? Is this compatible with the system at this time?
So that's one of the beautiful things about ADO.NET Data Services. So your client can have a view over the data, which can massage your entity appropriately. So if they have compatible schemas, they could use one class for defining the question view and one class for defining the answer view, as it were.
So I would be responsible for creating a property or an entity in my message object that said which type it was, and then I could just take
Yes,
care of
that
that
would be one of
myself.
the ways you could model that.
Okay, very cool. Thanks.
So, so time is like, time's up. Next, folks need to come. Sorry about that, but we can come here and we can talk about it. Also, we will be here. We will be here tonight at the Ask the Experts if you want to ask questions there, and we'll probably be hanging around the lounge area tomorrow, I guess, most of the day. So you can come talk to us about your questions, ideas, whatever you suggestions, whatever you have in mind. Thank you.
Thanks, everyone.